Hi everyone, we are from Group 1 who are going to do a presentation about problem-based learning main Group 1. For our presentation, first of all, I will going to introduce myself and my team members. My name is Tani Fan with metric number 206657. Next is Shang Weishen 205677. Ang Yifeng 207277. Lo Zhenzo 205793. And Song Shuke 200072. We have divided our presentation into 5 parts. First, we'll be looking at the history of FRITZ HABER. Second, the reaction involved in Haber process. Third, the hydrate of other elements in group 15. Fourth, the chemical and physical properties of hydrate of group 15 elements. And last is the usage of at least one of the hydrates of group 15 elements. Without further ado, let's get started.
Hello everybody, I'm Ang Fong, and now I will be presenting to you the history of FRITZ HABER. So before starting the presentations, do you think FRITZ HABER is a scientist or an army in total? So FRITZ HABER was born on 9 December 1868 and died in 29 January 1934. He was a German chemist who received a Nobel Prize in Chemistry in 1918 for invention of Haber's-Bosch process, a method used in industry to synthesize ammonia for nitrogen gas and hydrogen gas. So Haber was born in Breslau in a Jewish family. Haber was the son of Siegfried and Paula Haber. Siegfried is a person in the right diagram, while Paula Haber is Haber's mother, which is shown in the left diagram. So Haber's father, Siegfried, was a well-known merchant in town and operates a dye company, while her mother experienced a difficulty in pregnancy and died 3 weeks after FRITZ HABER birth. When Haber was about 6 years old, Siegfried remarried to Heinrich Hamburger. So for his early education, he attended primary school at Johannes School, and at the age of 11, he went to the St. Elizabeth Classical School, which is shown in the left diagram. And then for university, he studied chemistry in the Friedrich Wilhelm University in Berlin, which is shown in the right diagram. So during his time at University of Karlsruhe from 1894 to 1911, Haber and his assistant Robert Le Rossignol invented the Haber-Bosch process, which is a catalytic formation of ammonia from hydrogen and atmospheric nitrogen under the condition of high temperature and pressure. So in the left diagram, it shows the picture of Robert Le Rossignol. So the invention successfully is the production of nitrogen-based product like fertilizer, as at that time, the nitrogen-based product, to produce a nitrogen-based product, it only depends on the natural nitrogen deposit, so which is quite difficult to be found. So the invention gives a very great impact in nitrogen-based product productions. So in 1918, Haber was awarded the Nobel Prize in Chemistry for his work. So, but however, Haber became notorious in the upcoming World War I. He played a major role in the development of chemical weapons. So in his study of the effect of poison gas, Haber noted that the exposure to a low concentration of a poisonous gas for a long time often had the same effect as exposure to a high concentration for a short time. He formulated a simple mathematical relationship between the gas concentration and the necessary exposure time. This relationship became known as Haber's rule. The Haber's rule is Ct equals to K, where C equals to the concentration of gas, T is the amount of time necessary to breathe the gas to produce a given toxic effect, while K is a constant depending on both the gas and the effect. But however, his involvement in the development of chemical weapons make him to be notorious in the view of other scientists, including Albert Einstein and Ernest Rutherford. And for his marriage, his first wife is Clara Immerwahr on 2 May 1915. But however, she committed suicide in the garden by shooting herself in the heart with his service revolver. There's a conspiracy stating that Clara Immerwahr was very disappointed with Haber's involvement in chemical warfare, so which leads to her suicide. While her second wife is Charlotte Nathan, but both of them divorced in 6 December 1937. And on 29 January 1934, at the age of 67, FRITZ HABER died of heart failure in a Basel hotel in the mid-journey to receive research institutes. So this is the history of the FRITZ HABER. But however, do you think he is a scientist or an army that contributes to a war? Okay, thank you. That's all.
Wow, the history of FRITZ HABER sounds so interesting. Now, you may wonder what is Haber process. Haber process is one of the important processes in the world. This is because the ammonia that is produced by this process is used to make nitrogen-based fertilizer, which allow to grow all the food that we need every day.
The process combines a massive amount of nitrogen and hydrogen to produce ammonia. Nitrogen is easy to acquire because 78% of the air all around us is nitrogen, and we can easily get from there. And hydrogen derived mainly from natural gas. Two important things about this process are that it is an exothermic process, which a reaction is to produce heat. And it has two-way arrow, which means it's a reversible reaction. Some of the ammonia that gets formed will break down to reform nitrogen and hydrogen. The mixture of nitrogen and hydrogen going into the reactor is in the ratio of 1 molecule of nitrogen to 3 molecules of hydrogen. The catalyst used is ion catalyst, which is a substance that can increase the efficiency of the reaction. The optimum pressure for the reaction is 200 atm, and 400 degrees Celsius until 450 degrees Celsius is a compromised temperature producing a reasonably high proportion of ammonia in the equilibrium mixture.
Thanks to my partner. So now, Doctor, I will continue with the discussion of the hydrides of elements in group 15. So firstly, all the elements in this group form gaseous hydrides of the type MH3, which is ammonia, phosphine, arsine, CBi, and bismuthine. 3 of the 4 sp3 hybrid orbital overlapped with 1 s orbital of 3h atom to form 3 MH sigma bonds. 1 of the 4 hybrid orbital contain lone pair of electrons. In this group, all the elements are covalent in nature and formed by sp3 hybridization. Bond angle is directly proportional to the electronegtivity of the central atom. Due to the presence of lone pair electron on the central atom, this hydride acts as Lewis base. Hence, the basic character of these hydrides decrease down the group. After that, except for ammonia, they are all poisonous. All the hydrides are colorless gas. Okay, this is all from my part. Please let my partner to continue.
Good day everyone, I'm Chan Wei-shen. Now I'm going to discuss on question D, which is discuss the chemical and physical properties of hydrides of group 15 elements. All the elements in group 15, which is nitrogen, phosphorus, arsenic, antimony, and bismuth. Next, we have to know how elements in group 15 form hydrides. All elements of group 15 form hydrides of the type of EH3. E can be nitrogen, phosphorus, arsenic, antimony, or bismuth. So the elements here, they form hydrides according to the general formula here. So it's 2E plus 3H2 equals to 2EH3. So according to the table provided here, we can know that the hydride produced from nitrogen is ammonia, and phosphine is produced from phosphorus, arsine is produced from arsenic, and stibine is produced from antimony, and the last bismuthine is produced from bismuth with the chemical formula here. Touch on physical properties of hydrides, which are bond angle, stability, reducing nature, basic character, boiling point, and also solubility. Now let's talk about bond angle. The bond angle decreases down the group. Ammonia has the highest bond angle, and the bismuthine will have the lowest bond angle. This is due to the size of centrum atom increases down the group, so the lone pair will pull each other closer to one pair. So due to this, the bond angle will decrease. So next we will talk about stability. The stability of hydride depends upon the comparability of size. The order of stability of hydrides is, we start from ammonia, which is the most stable, and we end with bismuthine, which is the most unstable. This is because the central atom E increases in size down the group. With the increases in the size of the central atom, the EH bond becomes weaker. So we can refer to the table here. It shows that the atomic radius of the element in group 15 down the group increases. And we can also see the EH bond dissociation increases from nitrogen to bismuthine down the group. So with the increase in size, the overlapping between the orbitals of E and hydrogen will not be effective. And this causes the decrease in the stability of hydrides as we move down the group. Let's talk about reducing nature. When we look at the order of reducing character of hydrides, we can notice that bismuthine is a stronger reducing agent. As we move down the group, the size of elements increases, and the bond length and strength of EH bond also increases. Thus, the bond can break more easily to evolve hydrogen gas, which will act as the reducing agent. And in this case, bismuthine is the least stable among the hydrides. Hence, it can be the strongest reducing agent. Now, we will talk about basic character. Basic character here refers to the ability of molecule to donate its lone pair. And when we look at the order here, we can see that ammonia is the most basic and bismuthine is the least basic. Hydrides actually they act as Lewis bases due to the availability of a lone pair of electrons on the central atom. The basic character decreases down the group with an increase in the size of the central atom, and due to the large size of bismuth, the lone pair density is less closer to bismuth, and therefore the tendency to lose an electron decreases. The next one is boiling point. The boiling point here depends upon van der Waals forces, and this van der Waals forces increases with increase in size. So the order of the boiling points for 15 group hydrides is starts from ammonia, which has the highest boiling point, and ends with bismuthine with the lowest boiling point. So why ammonia has a higher boiling point than phosphine is because ammonia has hydrogen bonding inside it. And next we move to solubility. The order for the solubility same. We start from the ammonia, which is the most soluble, and ends with bismuthine, which is the least soluble. Ammonia has higher solubility due to the formation of hydrogen bonds too. Now let's move to chemical properties of hydrides. For the chemical properties, we will touch on the reactivity towards oxygen. Group 15 elements will form two types of oxide, which are E2O3 and E2O5. Nitrogen shows a strong tendency to form pi-pi bonds with oxygen, hence nitrogen forms a wide range of oxides. So nitrogen can form 5 stable oxides, which we can refer to the table here, which is nitrous oxide, nitric oxide, dinitrogen trioxide, dinitrogen tetroxide, and dinitrogen pentoxide. And for the other elements in group 15, like phosphorus, arsenic, antimony, and also bismuth, they can also form oxides, but only at the oxidation state at +3 and +5. While bismuth can form oxides in +5 oxidation state because of the inert pair effect. Oxides in the higher oxidation state of an element are more acidic than that of the lower oxidation state. Hence, the acidic strength of oxides of nitrogen increases from N2O3 to N2O5. So as we move down the group, the acidic character decreases, and in other words, the basic character of oxide increases on moving down the group. The last chemical property is the reactivity towards halogen. All the elements of group 15 form trihalides and pentahalides with the general formula of EX3 and EX5. So we can refer to the formula here and how it reacts with halogen to produce halides. And the trihalides produced are NF3, PF3, SF3, SPF3, and BIF3. All trihalides of these elements, except those of nitrogen, are stable. Phosphorus, arsenic, and antimony can form pentahalides due to the presence of vacant d orbitals in their valence shell. Nitrogen does not form pentahalides due to the absence of the d orbital in its valence shell, and pentahalides are more covalent than trihalides. The covalent character of halides decreases from nitrogen to bismuth. Thank you.
Now we'll talk about what is the usage of the hydride of group 15 element. In this presentation, we'll talk about the element of phosphorus, arsenide, and antimony. First, we'll talk about phosphine. Phosphine with a chemical formula of pH3. It used as a smoke screen. When pH3 is burned, it will produce smoke which is dense enough to serve as smoke screen. This is an example of the smoke screen. Next is used as a food fumigant. It used as an insecticide and rodenticide. pH3 is used indoor to control a broad spectrum of insects from non-food or non-feed commodity in sealed container or structure. Besides it, used in electrical and electronic products. It is doping agent for N-type semiconductor because the phosphorus is need to be introduced crystal. It also acts as the intermediate for the preparations of several flame retardants, and it also used in manufacture of photovoltaic cells. The next element is arsine, ASH3. Arsine is used in electrical and electronic products. It's fine. It's used in the semiconductor industry as a dopant. For silicon and germanium, arsine is an N-dopant in relation to phosphorus, in which it can increase the electrical conductivity. Arsine is deployed at 700 to 900 degrees Celsius to manufacture the semiconductor gallium arsenide by chemical vapor depositions. And then it also used in manufacture of certain glass die. And besides, it also used in soldering, galvanizing, burnishing, and lead plating. The next element is stibine, SbH3. Stibine is also used in electrical and electronic products. In the semiconductor industry, stibine is used to dope silicon with small quantity of antimony while the process of chemical vapor depositions. The high purity stibine can be used as an N-type gas phase dopant for silicon in semiconductors. It has also been used as a silicon dopant in epitaxial layers. Then stibine, they have two antimony compound that found during the productions of lead battery, which is in the casting of lead antimony trioxide and in the formations of lead stibine. And then stibine can also be used as a fumigating agents. Okay. That's all of our presentation. Thank you for watching.